Okay, hi everybody to this session of the Chilean probability seminar. And today we have the pleasure to hear Guillaume Blanc from Lausanne. He was doing his PhD in Paris, and now he's a postdoc of Johan Aro in Lausanne, and he will talk about random burning of Z2 grid, of the Euclidean lattice. So please, Guillaume, go ahead.
Thank you. Thanks for the introduction. So I was really looking forward to speaking about this. So thanks a lot, Dieter and Santiago for the invitation. This also means that it's the first time I give this talk. So too bad it's the one that will be on YouTube. But anyway, so that everything I will present today is based on joint work with Alice Contat. So we were office mates during our PhD. And she's now a CNRS researcher at Université Sorbonne Paris Nord. Okay, so let me start by telling you about the burning number, if you don't know what that is. So the burning number of a graph, of a finite graph G, is the minimal number of steps that you need to burn all of its vertices with the following burning procedure. So at each discrete time step I, you can choose a point, xi, to set on fire, and the fire propagates constantly at unit speed along the edges of the graph. Okay, so if at step I you set xi on fire, then by step k, what it will have burnt is the ball with radius k minus i, around it. Okay, so formally the burning number of G is the minimal k for which there exists x1 up to xk, such that the balls with radius k minus I around the xi cover the whole graph. So it's a graph parameter that was originally introduced by Alon in a 92 paper. So he presented it as a communication problem arising from Intel. And it was reintroduced more recently under the name burning number by Bonato, Jensen, and Roshanbin. So in 2016. Okay, so first calculation on the burning number. Let's calculate the burning number of the path on n vertices, Pn, and let's see that it's the ceiling of square root n. So if you call it k for short, then by definition of the burning number, there exists x1 up to xk, integers from 1 to n, such that the balls with radius k minus I around the points xi, they cover the whole path. And now if we take cardinalities in this equality, then you obtain that n must be at most the sum of the cardinalities of the balls. So n must be at most the sum of the 2k minus I plus 1. Because a ball in Z, a ball with radius r in Z, has cardinality 2r plus 1. Okay, so after calculation, n must be at most k squared, or in other words, k must be at least the ceiling of root n. And now for the upper bound, well, by monotonicity, it suffices to show that a path on m squared vertices, we can burn it in m steps. So here we have a path on m squared vertices. And if we guess that we can do it in m steps, then we know that the ball around the first points that we set on fire, x1, will have radius m minus 1. Okay, so let's choose this first point, x1, to be m. So that's, can you see my mouse? Okay, so that's on the left-hand side, it reaches exactly the point 1. So then on the right-hand side, it will reach exactly 2m minus 1. And if we take out the 2m minus 1 vertices of this ball from the m squared vertices of the path we had, then we're left with, well, a path on m minus 1 squared vertices. And we can continue like this. And a path with one vertex, of course, we can burn it in one step. And this shows by induction that the burning number of Pn is indeed the ceiling of root n. Okay, so a famous conjecture known as the burning number conjecture which was formulated by Bonato, Janssen, and Roshanbin in their 2016 paper, is that Pn has the maximal burning number among connected graphs on n vertices. So if at some point you're bored with my talk, you can always try to prove this burning number conjecture. Just be aware that it already has received a lot of attention from the graph theory / combinatorics community, and so there have been a lot of papers proving bounds, and quite recently there was this theorem by Norin and Turcotte, which showed that it holds asymptotically. So if we look at the max burning number over connected graphs on n vertices, then this is asymptotic to root n as n tends to infinity. Okay, so this was a quick introduction to the burning number if you hadn't heard of it. And now we're probabilists, and we want to consider some random burning processes. So this was first done by Mitsche, Prałat, and Roshanbin. And so a piece of notation, so given a sequence, x1, x2, and so on, will denote by a burnt k of x1 up to xk, the set of vertices burnt by x1 up to xk when we look at step k. So it's the union of the same balls as before. So what we want to do now is consider the burning process associated with some sequence, capital X1, capital X2, and so on, of random variables with values in V, and the associated random burning number, tau, so the first step at which the whole graph is burnt by these random variables. So it is itself a random variable whose distribution is determined by the distribution of the sequence, x1, x2, and so on. And we will consider two natural choices for that sequence. So first natural choice is to look at x1, x2, and so on, independent and uniform. So in this case, we'll call the corresponding random burning number, so the first time at which the whole graph is burnt, the coupon collector burning number of the graph. We'll denote it by tau cc of g. So the words I will explain later. And another natural distribution that we can take for the sequence of points that we set on fire at each step is, so let me call them y1, y2, and so on in this case, is to choose it in such a way that the law of the next point that we set on fire, conditionally on the past, is the uniform distribution on the complement of the set of vertices burnt by the previous points. So this, I'm telling you what happens provided that the complement is not empty. But of course, if already everything is burnt, that I don't need to tell you anything about the law of the next point I set on fire, everything will remain completely burnt. Okay, so in this case, we denote by tau rs of g, the corresponding random burning number, the first step at which the whole graph is burnt, and we call it the rejection sampling burning number of the graph. And as I just said, its distribution is uniquely determined by the condition on the law of the sequence y1, y2, and so on. Okay, so this was done by Mitsche, Prałat, and Roshanbin for our friend Pn, the path on n vertices. So recall that its burning number is ceiling of root n, and so for the coupon collector burning number first. So tau cc of Pn, recall, is the first step at which everything is burnt, the whole path, when we consider independent uniforms. So they've shown that this tau cc of Pn is asymptotic to square root of n log n over 2 in probability. And so root n is the correct order for the real burning number. Here there is an extra log. There is kind of a geometric coupon collector phenomenon here, and which is explained by the fact that near the end of the process, when almost everything is burnt, you have to wait for a long time. When almost everything is burning, you have to wait for a long time until one of the uniforms you're sampling just falls into the unburnt region. So this explains the extra log, which shouldn't be here, let's hope, in the rejection sampling case. Okay, so now we consider the tau RS of Pn, so the first step at which the whole path is burnt when the law of the next point we set on fire conditionally on the past is the uniform distribution on the complement of the set of points burnt by on the set of vertices, sorry, burnt by the previous point. So I will try to say points for those I set on fire and vertices for just the vertices of the graph. Okay, so here they've shown that tau RS of Pn indeed has the correct order root n in probability in that sense. So this achieves the same order as the real burning numbers. Okay, so with Alice we wanted to do the same thing in the discrete Euclidean torus with side length n in dimension d. So T and d. We wanted to study the asymptotic behavior of tau cc T and d and tau RS T and d as n tends to infinity. So what's known? Well, we've just seen what happens for Pn, and between Pn and Tn1, there's just one extra edge that you add, and so the results of Mitsche, Prałat and Roshanbin, they also apply for Tn1. So we already know that the coupon collector burning number is asymptotic to square root of n log n over 2 in probability, and that the rejection sampling burning number is of order root n in probability in that sense when d equals 1. All right, and also for general d, to know what we're up against, what's the order of the real burning number of T and d? So again, from Pn to Tn1, you only have one extra edge to add, and this doesn't affect, in fact, the burning number. So B of Tn1 is also ceiling of root n. Then in dimension 2, so the burning number of Tn2 was calculated asymptotically by Mitsche, Prałat and Roshanbin in the same paper. So they've shown that it's asymptotic to this explicit constant times n to the 2 over 3. And then for general d, so to the best of our knowledge, the analogous result for general d is not known. So with Alice, we contented ourselves with showing that the burning number of T and d is of order n to the d over d plus 1. So don't spend a lot of time reading the constant gamma d. It's for sure not the right constant, but at least in dimensions 1 and 2, the lower bound, so the constant alpha d, is the right constant. So alpha 1 is equal to 1, and alpha 2 is equal to this constant. So we did not prove that that alpha d is the right constant for general d. Okay. Okay, so before I state our main results, so here are some pictures. So here are two simulations of the coupon collector and the rejection sampling burning processes in T202. So on each picture, the points are colored from dark to bright according to the first time at which they became burnt. So the darker they are, the earlier they became burnt, and the brighter they are, the later they became burnt. Okay, this is another simulation. And now, so let me come to our main results, starting with the asymptotic for the coupon collector burning number of T and d. So the first step at which the whole torus is burnt by independent uniforms. So we proved the same kind of the analog of the result of Mitsche, and Roshanbin in dimension 1. So tau cc of T and d is asymptotic to this explicit constant beta d times n to the d over d plus 1 times an extra log n to the 1 over d plus 1 in probability. And the explanation for this extra log is the same as before. We have a geometric coupon collector effect at play here. Hence the name of the burning process, by the way. Okay, and now for the rejection sampling burning number. So now the first step at which the whole torus is burnt when the law of the next point we set on fire conditionally on the past is the uniform distribution on the complement of the set of vertices burnt by the previous points. So we find that tau rs of t and d is asymptotic to t times n to the d over d plus 1 in probability, where t is a constant that depends on the dimension d, and that we identify as the explosion time of the maximal solution y to the generalized Blasius equation, which is that ODE, that Cauchy problem. Okay, so if you remember, so this is a Cauchy problem. So it admits a unique maximal solution, which may be defined either on the whole of R plus, or which blows up in finite time. And here it is the case, it blows up in finite time, and we denote by t its explosion time. And this is the constant that we get in the limit. Okay, and again, we find that it achieves the same, that the rejection sampling burning process achieves the same order as the real burning number, which is n to the d over d plus 1. Okay, so another related result about the rejection sampling burning process is the following functional convergence result for the set of unburnt vertices. So let me denote by Bn Rs of k, the set of vertices burnt by y1 up to yk at step k. So we prove that the density of the complement of Bn Rs, so the set of unburnt vertices, its proportion in the torus. If we look at it at step floor of t times n to the d over d plus 1, so t can vary between 0 and capital T, the explosion time we had before, we find that this density converges in probability to 1 over yd of t. So yd is the dth derivative of y, and y is again the maximal solution of the generalized Blasius equation, which is that ODE. Okay, so since y and its derivative, they all explode near the explosion time, and so 1 over yd is something that goes from 1 to 0 between time 0 and capital T. So we find that what we would expect, the density vanishes. Okay. Right. So maybe let's see things more clearly on the d equals 1 example, where actually the generalized Blasius equation in that case becomes that ODE, which in fact is explicitly solvable. So we find that capital T is pi over 2, and y is simply the tangent function. So if we specify the previous theorems to d equals 1, we find that tau rs of t and 1 is asymptotic to pi over 2 times root n in probability, and that the density of the complement of BNRS at step floor of t times root n for t between 0 and pi over 2, it converges to cos t squared. And indeed, cos t squared is something that goes from 1 to 0 between time 0 and pi over 2. Okay, so the same thing happens for general D, but just the solution is not explicit anymore, at least to the best of our knowledge. Okay, so let me try to explain, to give a heuristic for this for the last two statements. And for this, let's try to define a continuum burning process that will mimic, so that will be designed to mimic the rejection sampling burning number on T and D, but seen from far away. Okay, so for this, we fix a function, fn, defined on some interval 0 Tn, and we consider a Poisson process, pi n, with intensity dx times fn of t dt on td times 0 Tn, where this time td is the continuum Euclidean torus with side length 1. So what do we do with this pi n? So for each atom xt of pi n, we will set the point x on fire at time t, and we will imagine that the fire propagates constantly at speed 1 over n with respect to the metric on td induced by the 1 norm on rd. So why do we do this? Well, we want to mimic the rejection sampling burning process in T and D, but seen from distance n. Okay, so now the torus has size 1, and the fire propagates at speed 1 over n. Okay, and in this continuum burning process in TD, the set of elements of TD that are burnt by time t is now this Bn of t, the union over the atoms excess of pi n, which have an s which is at most t, the union of the balls with radius t minus s over n around x. Okay, so for now, fn is still a parameter that we have to choose. And remember that we want to mimic the rejection sampling burning process in T and D seen from distance n. So now we will design the function fn so that at each time t, on average, the process pi n puts 1 point per unit of time in the unburnt region, which is the complement of B and T. Okay, so let's formalize this. So let's calculate the expected density of the unburnt region, the complement of B and T. So it's this integral of the probability that Z does not belong to Bn of T. And now this probability, so the probability that a given point Z in T and D is not burnt by time T in this continuum burning process, what is the probability that there is no atom xs of the process pi n, for which S is at most T, and X belongs to the ball with radius T minus S over N around Z. So it's the probability for this Poisson random variable to be 0. So it's exponential of minus its parameter, which is this integral, which in fact we can calculate further. So we find altogether that the expected density of the complement of Bn of T, it's equal to this negative exponential that involves the function fn. Okay, and now we want to adjust fn so that it compensates this negative exponential. So that on average, the mean, so that on average, sorry, pi n will put 1 point per unit of time in this unburnt region, the complement of Bn of T. So we want this equality to hold for all values of t between 0 and capital Tn. And so I will skip the details here, but this entails that fn of t is the following time change of yd, so at speed n to the minus d over d plus 1, where so yd is the dth derivative of y, which is the maximal solution of the same equation we had before. Okay, so let me conclude this heuristic. So we find that Tn, so the total duration of the continuum burning process that we designed in order to mimic the rejection sampling burning process in T and D, seen from far away, this duration time is exactly equal to T times n to the d over d plus 1. And moreover, the density of the complement of Bn at time t times n to the d over d plus 1, at least in expectation, is exactly equal to 1 over yd of t. Okay, so this, I hope, is explains these two results. So this is for the total duration time, and this is for the density, which we find to be 1 over yd. Hop. Voilà. So yes, and that's so it's this this heuristic that that led us to the results. And one thing I went over quite quickly is this this equation. So I said, oh yes, y is the maximal solution of the generalized Blasius equation. So in fact, with Alice, we had to study it. So in particular, in the proofs later, although I will not explain this, we had to know some asymptotics of y and its derivatives near the explosion time. So I won't tell you about this today, but if you're looking for an ODE problem for your students, then let me advertise our paper with Alice. Okay, so that's it for the presentation of the main results, and I think it's a good time for questions if you have some up to now. Oh, otherwise, okay. Otherwise, I'll just go on. So let me tell you about some of the proof ideas. Starting with the asymptotic for the coupon collector burning number of T and D. So the first time at which the whole torus is burnt by independent uniforms that I call x1, x2, and so on. And I will denote by BNCC the associated burning process, defined like that. Okay, so here is the asymptotic we are after. I show it again, and so the proof of this asymptotic is based on a first and second moment argument applied to the random variables cardinality of the complement of BNCC of K. So why is that? Well, the event that tau cc of T and D is strictly larger than K is equal to the event that the complement of BNCC of K has strictly positive cardinality, right? Both events are saying the torus is not entirely burnt by step K. Okay, so let's take the expectation of that random variable, the complement of BNCC of K. As in the continuum, we can express it like that in terms of the probabilities that points do not belong to BNCC of K. And the probability that a given point X does not belong to BNCC of K, we can calculate it as before in the continuum. So it's the probability that for each I between 1 and K, the point Xi does not belong to the ball with radius K minus I around X. Right, but x1, x2, and so on are just independent uniforms. So we obtain in the end this product, and now it's time to do some asymptotics. Okay, so in hindsight, we look at it at step Kn of C. So C is a parameter, and Kn of C is C times n to the d times this extra log, all of this to the power 1 over d plus 1, and we take the integer part. Okay, so the probability that x does not belong to BNCC at step Kn of C, which is this product, now we find that it's approximately equal to this exponential of minus the sum. So the sum of the cardinalities of the balls over n to the d. But we're doing some asymptotics. And if you look at a graph distance ball in ZD, well, its cardinality with the large radius r is asymptotic to 2 to the d over d factorial times r to the d. So 2 to the d over d factorial, in fact, is the Lebesgue measure of the L1 ball in R. Okay, so now we have just a sum to evaluate asymptotically. So we find that this probability is approximately equal to the exponential of minus 2 to the d over d plus 1 squared times kn of c to the d plus 1 over n to the d. Right, but by the definition of kn of c, everything cancels, and we're left with an exponential of minus this constant, the parameter c, and log n. Okay, so if we get back now to the expectation of the complement, of the cardinality of the complement of BNCC, we find that at step kn of c, it's approximately equal to, so here let's say asymptotic to n to the d times the same negative exponential that we had before. And now if we try to run, so now we want to know when does the negative exponential beat n to the d. So when does this constant, 2 to the d over d plus 1 factorial times c, is larger than, well, d. So this is if we run, let's say, a basic first moment argument, if we bound the probability that the cardinality is strictly positive by the first moment. So here we would find that the probability goes to 0 as soon as c is larger than that threshold. And I don't expect you to remember, but the actual threshold I claimed is c star is off by a factor of d plus 1. So the actual threshold is smaller. The whole torus is bound before. So luckily, the second moment calculation gives us the right threshold. We don't have to improve it. But if we believe the second moment calculation to give the right thing, then at least we need to improve this first moment argument. So how can we do that? Well, what we can do is take a covering, a smart one of the torus by balls of radius Rn. Let's say Rn is n to the d over d plus 1 with integer parts. So I will index the centers of the balls, the x's, by some set an, and I want the covering to be smart in the sense that we can choose it so that the cardinality of an is at most of the order of n over Rn to the d. So in other words, n to the d over d plus 1. So what do we do with this covering? Well, if every point x in an is burned at step kn of c, then, is burning by step kn of c, then if we wait just another Rn steps, then the whole torus will be burned, because the balls with radius Rn are on these points, they cover the whole torus. So this translates into the following inclusion of events. And if we take the probability in this inclusion, we find that, so the probability that tau cc of t and d is larger than kn of c plus Rn, we can bound it by this sum of these probabilities that we estimated before. And now the upper bound we get is at most of the order of n to the d over d plus 1. This is for the cardinality of an. And the same negative exponential as we had before. This is for the probabilities. Okay, and now good news. This exponent, 2 to the d over d plus 1 factorial times c, now it only has to beat d over d plus 1, whereas before it had to beat d. So this is how we get rid of the extra d plus 1 factor. Okay. Oh yeah, and finally, so kn of c is n to the d over d plus 1 times some extra log. So Rn, which is n to the d over d plus 1, is negligible in comparison. So the plus Rn does not affect the asymptotic for the time at which everything we claim is burned. Okay. So this was for the coupon collector burning process. And now let me tell you about the rejection sampling burning process. So the first, the starting point of our proof was to construct an instance of the rejection sampling burning process Well, by using rejection sampling, hence the name. It only comes up now, which, by the way, is exactly what you would do if you wanted to simulate the process, right? Okay, so the idea is to remember the sequence y1, y2, and so on that we had before. We can construct it by induction as follows. So for each k, such that y1 to yk have been constructed, we construct the next yk plus 1 as follows. We sample independent uniforms on the torus until we find one that does not belong to the set of points burnt by the set of vertices, sorry, burnt by the previous points. So if we find one, we call it yk plus 1. So in particular, y1 is just a uniform on the torus. There is no condition before time 0. And also, yes, we fix some arbitrary convention if we cannot find such a uniform, which is the case, for instance, if already the whole torus is burnt. Okay, and the claim is that, well, the burning process, let me call it BNRS as before, associated with these random variables y1, y2, and so on, defined in this way, is an instance of the rejection sampling burning process I was talking about before. Okay, so let's see it on an example. So actually, to simplify, let's not look at the torus. Let's forget about periodic boundary conditions and let's look at the grid. Here is the square grid and n equals 5. And I want to sample the points that I will set on fire. Okay, so this is for step 1. I sample a uniform. The corresponding vertex is not burning, so I can set it on fire, and this is the end of step 1. Okay, now comes step 2. I sample a uniform. At bad luck, the corresponding vertex is already burning. So I want to sample, so I discard it, and I sample another one, another uniform. And good luck, the corresponding vertex is not already burning. So we set it on fire. And let's not forget also, so step 2 is not finished yet. We also have to propagate the fire to neighboring vertices. Okay, now these are the points that just became burning. And now comes step 3. Again, we sample a uniform. Bad luck, again, it falls on a vertex that's already burning due to the previous steps. So we discard it and we sample another one. And good luck, we can set it on fire. And we also don't forget to propagate the fire to neighboring vertices. Okay, so I hope this is clear. And also with the same idea, so in the same spirit, here is another thing that we can do, another construction, let's say. So if we're given a sequence A and K of random subsets of T and D, then we can in the same way construct a sequence Z1, Z2, and so on of random variables by induction as follows. So again, for each k, we will construct zk plus 1 in the following way. We'll sample independent uniforms on the torus until we find one that does not belong to an of k. And we will call it zk plus 1. And again, we have to come up with an arbitrary convention if we cannot find one, which is the case, for instance, if an of k is already equal to td. Okay. And we can also consider the burning process Bn associated with this sequence Z1, Z2, and so on that we have constructed in this way. And just to explain where this comes from, so if we do this with An, which is the BNRS I was telling you about before, and with the Z1, Z2, and so on, that are the Y1, Y2, and so on, I was telling you about before. so the same procedure, then we obtain that Bn is the same BNRS. So maybe if I can rephrase it, to sample the points I will burn to obtain Bn, I sample with rejection in the complement of An. And if I take An to be BNRS, then when I sample with rejection in the complement of BNRS, well, what I get as the corresponding burning process is BNRS by definition. But also, what's good with this construction is that we can also decouple. So we can also, I think it's more clear on the next slide. So using this idea, we can construct by induction a sequence BNP of intermediate burning processes. So let me construct it before and tell you why after. So I start with Bn0, which is just the trivial burning process, which is always empty. And then for each P such that Bn0 up to Bnp have been constructed, we can construct Bnp plus 1 as the burning process associated with the sequence Z1, Z2, and so on of random variables that we construct by induction in exactly the same way as before. So for each k, we construct zk plus 1 by sampling uniforms on the torus until we find one that does not belong to Bnp of k, and we call it zk plus 1. Again, we have to fix an arbitrary convention if we cannot find one, which is the case, for instance, if Bnp of k is already the whole torus. But the point here is that to obtain Bnp plus 1, the points I sample, I do not sample them with rejection within Bnp plus 1 itself. I sample with rejection in another one, which is Bnp. So that's what I meant earlier by decoupling. And for instance, just to clarify, if we look at Bn1, so Bn0 is always empty. So when we sample the Z1, Z2, and so on in the way that's described here, well, the Zi's actually are just independent uniforms on TND. So what I'm saying is that Bn1 is an instance of the coupon collector burning process. Okay, so maybe I've already said the word coupling, but now here comes the real coupling. So now we want to use the same uniforms between different values of P. We want to use the same uniforms. And if we do that, then the intermediate burning processes, BNP, that we have just constructed, they will be nested. So Bn0 will be inside Bn1 and so on. Okay, and moreover, we can also couple them with the rejection sampling burning process BNRS that we had before. Again, if we use the same uniforms for different values of P and also for BNRS. So in this way, you obtain such nested burning processes. And in this coupling, so the intermediate burning processes B and P that we have defined, well, they interpolate between the trivial burning process, this is for P equals 0, the coupon collector burning process, this is for P equals 1, and the rejection sampling burning process, BNRS, which morally we get by sending P to infinity. Okay, so what perfect, but what have we gained here? So recall, we want to show the following functional convergence result. So we want to establish that the density of the complement of BNRS, when we look at it at speed n to the d over d plus 1, it admits a limiting density which is 1 over yd of t. So it's hard to do on BNRS directly at once, but But we have this key lemma that I will explain now. So let's take the same setting as before. So we have a sequence of random subsets of T and D, A and of K. And we have a sequence of random variables, Z1, Z2, and so on, that are constructed by induction as we did before. So for each K, Zk plus 1, to obtain it, we sample independent uniforms on the torus until we find one that does not belong to A and of K, and we call it Zk plus 1. And we consider the burning process Bn associated with Z1 up to, I mean, the sequence of Zi. So what does the key lemma say? Well, it says that if the complement of An admits a limiting density at speed n to the d over d plus 1, admits the limiting density 1 over f at speed n to the d over d plus 1, then so does the complement of Bn. So it will admit a density 1 over g at speed n to the d over d plus 1, where g is given explicitly in terms of f by this expression. Okay, so actually once we have this lemma, we can apply it to this sequence of intermediate burning processes, B and P. We apply it by induction, and we obtain the following functional convergence result for the density of the intermediate burning processes B and P, the density of the complements. We find that in the limit it's given by 1 over Fp, where Fp is the sequence of functions defined by induction as follows. So F0 is just constantly equal to 1 on the whole of R plus. So this corresponds to the density of the complement of the trivial means empty burning process. And for each P, Fp plus 1 is given explicitly in terms of Fp by the same expression as we had in the lemma. So maybe I can flash you again the lemma. So it's saying that if we know that the complement of An has a limiting density 1 over f at speed n to the d over d plus 1, then we get that the complement of Bn has speed 1 over g. G is that at speed n to the d over d plus 1. And this is exactly what we have for B0 first. And then we can go from BNP to BNP plus 1 using the key lemma. Okay, so this explains the functional convergence result we get for the BNP. And now remember that the intermediate burning processes B and P, they interpolate between the trivial burning process for P equals 0, the coupon collector burning process for P equals 1, and the rejection sampling burning process that we get morally as P tends to infinity. And in fact, the functions Fp that we iterate before, it turns out that if we restrict to a compact subinterval of 0t, so capital T is again the explosion time of the maximal solution of the generalized Blasius equation. So if we restrict to this compact subinterval 0 tau, well, the functions Fp, they converge uniformly to the YD. So that's how we go from the limiting density of the complement of the BNP, which is 1 over Fp, to the limiting density of the rejection sampling its complement burning process, which is 1 over YD. Okay. Right, and I just said this is how. There are some details So there is basically an interchange of limits that we need to justify here between n and p. But I won't talk about this today. Okay, so let's say we have this this functional convergence. How do we get to the asymptotic for the rejection sampling burning number? So the first time at which the whole torus is burnt. So there is one direction which is an easy consequence of the functional convergence, is the lower bound for this. So why? So if we fix some epsilon, the probability that tau rs of t and d over n to the d over d plus 1 is at most t minus epsilon. So it's the probability that already at time t minus epsilon times n to the d over d plus 1, everything is burnt. So it's the probability that the complement of BNRS at this time is 0, right? But what we know is if we divide here by n to the d, we know what's the limit as n tends to infinity of the density of the complement of BNRS at time t minus epsilon and at speed n to the d over d plus 1. So actually this limiting density will be 1 over yd of t minus epsilon. Doesn't matter what it is, it's something strictly positive. So if we want this to be 0, then this means that the density of that has to deviate from its limit by a given positive real number. And this convergence in probability is saying that this happens with a vanishing probability as n tends to infinity. Okay, so the lower bound is an easy consequence of the functional convergence. And for the upper bound, an extra ingredient is required. So I won't explain it in detail, but let me tell you the idea. So we start again from the functional convergence, which tells us that slightly before t, so at time t minus epsilon times n to the d over d plus 1, we have a small proportion of unburnt vertices. And once we know that this is small, we have to show that even if it means adding some more steps, as long as they will not matter in front of n to the d over d plus 1, we can burn everything by rejection sampling. Okay, so that's it for me, and thank you for your attention.
Questions for Guillaume?
Yes, I have one.
Please.
Hey, Guillaume, very nice talk. Thank you. I'm sure
Thanks.
you'll do YouTube proud. I was wondering about this first moment method that you had in the case of the coupon collector burning.
Yeah.
There you said that if you add this little quantity Rn, which is negligible compared to this Kc, then you can show that with this improved covering, that this probability tends to 0. So I was wondering if you think about, say, the second order fluctuations of the collector, do you think that this will be of the order Rn, so n to the d over d plus 1?
But it's a very good question. I don't know actually. So we've not tried to improve these into we've not tried to identify the second order, but it's a good question. So maybe there's a related process where it might be slightly simpler, but I'm not sure, is if all the balls have the same radius. So if you throw k balls with the radius k, and you look at the first k for which everything is covered. So this has been looked at, I think, by Augusto Teixeira and a co-author, I don't remember who. But I mean, there are variants of these processes for which the second order might be known, but I must admit I don't know. Maybe it could also be
Because
doable
also
for.
does this with these random coverings, right? Where you sort of show or throw random shapes at the torus, and then you want to ask how long does it take until it's completely covered.
Yeah.
Yeah. I know the guy with who we did this. Yeah. Oh, nice. That's interesting. Thanks.
Other questions?
So I have a question which is related to Bas's question. But do you have any idea of what the second order should be for the burning number, for the actual burning number?
Well, we don't even know the first order, but in D.
No, we know.
So
No, for dimension 2, you mean, Santi, no?
for dimension 2.
Yes.
So maybe Dieter, you know the correction,
No,
the second order?
I don't know.
Okay. Well, me neither. But for D equals 1, it's either 1 or 0.
Okay.
Because you have the ceiling part and well.
Okay, just to see whether this Rn makes a difference or not. Maybe you have okay, maybe this knowing the second or the expected, I don't know, second order term could be helpful. Okay, very nice talk.
Thank you.
Yeah, very nice, Guillaume, indeed. But is there an intuition why this Rn should be actually the order of the second order, since Bas asked this already? I mean, it's bound only,
no,
but I don't see a reason for being the second order.
No, I didn't say it should be the correct thing. Actually, we're not even sure that this proof, this method should give you an argument for the. I mean, maybe we can improve. No. Well, I don't know.
Yeah, did you? So you tried? Is this the optimal trade-off between the size of AN and Rn? Is this optimal in the sense of the second order term? Did you try this?
So it's optimal in terms of exponents, but that doesn't answer your question, right?
Okay.
I mean, if I put Rn to be n to the alpha, then if alpha is anything else than d over d plus 1, I won't get the correct bound.
Yeah.
But
this AN, size of AN, you choose it when of exactly Rn to optimize, or is this?
Okay. Maybe I should have stated that differently. So no, so actually we're just if TND is a box, we're just dividing it into n over Rn to the d boxes with side length Rn to the d. But I'm just doing that like in the continuum, but maybe it's more clear with boxes in the discrete.
Right.
I don't know if that
These are all of the
answers.
same size, that you might lose something, right? Because perhaps you could take some larger balls and some smaller balls, no?
Yeah. Yes. Saying that x1 we ask it not to be burnt by time, blah blah blah. X2 different thing. Yeah, maybe. Yeah.
This could be a factor 2 at least for this for the second order term, I would guess, no?
Okay, maybe, yeah.
Yeah. Okay. Other questions?
Question? Thanks for your talk. I just want to ask if you introduce some firefighter vertex, like you're burning at the same time you have firefighter to, and how, like, is there some story about it?
Not that I know. So I know that there are other processes with firefighters, maybe? No, Dieter,
It exists.
you studied them, right? But I must admit, I don't really know what happens in that case.
Okay, yeah. Thank you.
Yeah, it exists. I don't know the relationship.
I had a question. If you introduce a bias like proportional to the distance to the burning area to some power s when choosing the next point you want to burn.
Yeah.
Can you still use your technique to get some sort of similar result?
You can still do rejection. You can still do rejection if you toss a point with a uniform and play a game.
Yes.
Maybe. So I would have to look maybe first at the coupon collector and then at the key lemma, because everything is in there. So to establish this, will it also work if the zi are not anymore uniform, but want to avoid a... Well, it's a good question. It might be the case, but I don't know for sure right now. Sorry.
Thank you.
Wouldn't that point process that you started with, this sort of heuristic argument that you gave, wouldn't that have to change somehow? If you would use
Oh
a
yes,
different
yeah, for sure.
starting method, right?
Yeah.
Then yield
Yeah,
something.
right. We should start with the heuristic and not the key lemma. You're right. Yeah. But well, I don't know. I think I don't know how to make the heuristic then. But then we're screwed. Maybe. If I go back to the... So what I am... Yes, what we're using in the heuristic is that so you see there is no unique way to say that Fn has to be designed in that way. So we're saying we look at it so that on average, blah blah blah, and then we calculate the expected. So maybe this is not something you can do anymore. I mean, this approximation of saying that everything is homogeneous if you start having some special correlations like this. Thanks, Bas. I don't know if this answers the question.
Thank you.
I do have another question, if I may.
Sure.
Actually, about this heuristic, because it's kind of surprising that this density of this point process pi n, which I think was on the previous slide.
Or
a bit before.
This one? Sorry.
No, a couple of slides back, maybe number 18.
Okay, the intensity measure.
Yes,
this one?
yeah, right. But the intensity, it doesn't depend on space, right? So you don't really see that you're rejecting anything there.
I didn't explain that. Sorry. Yeah. So the first idea we're using by doing that is that the points that the process puts in the region that's already burning, we don't care about them. We can put them anyway, and they will just not contribute.
Okay, right.
That's why we only have to adjust the intensity to blow up the intensity in the right way, so that on average we place 1 point per unit of time in the unburnt region.
Okay. So you kind of do
Sorry, I didn't
collector,
explain that.
but you have sort of the intensity in time increases so much that it's as if you were doing rejection sampling.
Exactly. Yes, we could also do it in the discrete, I guess. It's just that it's less nice to write down, I guess.
Sure. Yeah.
Because you have to say at each step, I want to go up that far in some tower of independent uniforms.
And in these intermediate point processes with P is 1, P is 2, and so forth, do you have some kind of geometric interpretation when P is not 1 or infinity?
No. Just they're convenient. Yeah, actually, we don't say anything more than what's the limiting density of the complement at speed n to the d over d plus 1. So we're just speaking about cardinality, not even geometry.
Okay. Well, if any more questions? Otherwise, I suggest we thank Guillaume again for this nice talk.
Thank you.